Hello class, we continue our lecture 12 on heat, work and application for rotational vibrational energy. So I'm going to complete half part of this. Let us recall average energy and differential first. So the way we define average internal energy is given by this one, okay? So you have average internal energy, you sum over the multiplications of Boltzmann probability distribution okay, times the energy eigenvalues. Remember, energy eigenvalues. Alright, so next what we have, probabilities of the system in each quantum state. Remember, we always look at the accessible quantum state. Okay, we have is given by your Boltzmann probability distribution here, and you know that Z is your partition function. Maybe in a good way, let me stick Z with Z, okay, Z as a proper notation. Okay, then we want to look at changes in average of your internal energy U. So what is as a given? So your U here is somehow like your U are functions of state of probability and energy eigenvalue. So you do differential. So the differential is first you do the first term like partial change over the probability. So you fix your energy eigenvalue. On the second term, you change on the energy eigenvalue, you fix the probability. Okay, that's why this part is depicted in these two figures. Okay. For increasing your internal energy, average energy, you adding heat, okay. And the other one is you make your another one is you keep, okay, no change in terms of energy eigenvalue, but you change, you look at the length of your probability, and so look at the length, alright, compare with number 1 and number 2. So this comes from what? So this comes from you change that, fix. This comes from you fix, you change internal energy. So you do either that, okay, both energy levels and probabilities will be changed, okay. If changes in energy levels and probabilities are not small, then you cannot identify heat and work separately. So if it's big, okay. Now we go into mechanical work and other types of work. It is very much important how we produce work, okay. So what are the system we are going to look at? Now we look at a system of the following. Change in energy levels, see, change in energy levels of gas atom in a cube of volume. Let's say you have a cube of the same length, okay, volume L. So you can get your L here is equivalent to V to the power of 1/3, okay. The energy eigenvalue is given by this equation, okay. You have, because it's three-dimensional now, 3D, because it's a cube, okay. That's why you have it's related to motions of particles in a box, okay. So if in 1D, or if you consider 2D, all right, you can do that. So this one give you plain. So the energy level, energy eigenvalue is given to you. So let's say you want to find a change of your eigenvalue. So this is your eigenvalue respect to volume. So that was just by you substitute here, then you define that it is given by minus 2/3 multiplied by eigenvalue I over V. Okay, so given that previously you have the total of energy is the sum of all your eigenvalues. Okay, that gives your total energy. So the change of your total energy over your volume is thus given by the same thing. Okay, now let's look at the mechanical work by look at the changing of over volume. Okay, so work is given by this form of minus P dV. Okay, so you make this equivalent to where your work is contributed by change in your energy eigenvalue here. So this is coming from before, okay, the system. All right, you fix the value volume. So you see the probability here. So what does it mean? You have come to this. Okay, so you can rewrite this is equivalent to the changes of your total energy. All right, so you just substitute the partial derivative respect to V. Of course, this is coming from dV from your total differential. So you apply that. You can take out the constant, of course, and you see that from my my green box, they are eventually equivalent. So it means what? The multiplications between the pressure and the volume respect to the internal energy, okay, for this particular system is 2/3. Okay, all right, that is the mechanical work by change over volume. Okay, so now the most important part over here, if we look at other types of work, so this is a little bit tricky, more practical. Okay, so we look at the coupling of external parameters with the change of eigenvalue. Okay, for example, first we have this what we call Zeeman effect. So what is Zeeman effect does? So they have a coupling magnetic induction field to the energy eigenvalue respect to the gas of atom, right? Second one, Stark effect, okay, for which you look at the effects of your electric field. So this is the common electric field and this is like the common B, okay, vector to a gas of atoms that shifted energy of gas atom with electric field. So you see there's a shifted energy here and there's the coupling or magnetic induction. So this gives you change over energy like this. Okay, and one can do cannot do a much more simple calculations. Actually, we can do much more simple calculations. Okay, instead, if we do classically, like classical electromagnetism, you have to solve the integral. So this come from, okay, but over here you just look for your partition function, and then you can solve using Boltzmann distribution. So integral will apply classical way. All right, so now let's look at the system. So the system is given your energy eigenvalue that depends on volume of the sample V on a uniform magnetic induction field B. So it means that your B here is just uniform towards Z direction. Okay, you can treat your total energy as a state functions in respect to volume and magnetic induction field like this one. All right, so changes in the energy, so this is your differential. Remember we learned this from your earlier class, okay, total differential, okay, of two variables, and you can calculate at least a magnetization. So magnetization is another state function, okay, and the magnetization is given by equation 1. you have minus 1 over v, and you sum over. I think there's a mistake over here, so you have, let me do this, so you have pi, then this is your I. Okay, let me fix this. Okay, good. Now using the given above, let's say you have n particle spin half particle with energy eigenvalue, okay, is given by plus minus mu bz. So usually your mu here is your permeability, okay. So if you've learned electromagnetism before, you have mu permeability if electricity permittivity. This is the one that measure how that measure the strength of your materials towards magnetic field or electric field. Okay, what can we do to compute? The aim is to compute magnetization. You can calculate using Boltzmann probability distributions. That give you eventually your magnetizations give you by equation 2. Okay, how? Actually from the notes, it's an exercise, you can prove this if you want, but the tip is you're using the Boltzmann probability distribution, okay, where your E total energy is given by plus minus mu bz, and then your partition functions is just the sum of your probability. If you substitute, this is number 1, 2, 3 accordingly, alright, and you can obtain equation. To stop. Okay, okay class, so for the other parts I will prepare another video perhaps. Let's see. Okay, thank you.